Oh, one thing that I did want to mention is this exam will cover material since exam 1. So it'll be sections 5.2, 7.4, 8.1, and 8.2. The content we've covered after exam 1. There won't be any specific problems from content before exam 1 on this exam. Obviously, some of the things we did before exam 1 might resurface, anytime we're working with fractions. Well, maybe we did some work with fractions in the early part and we're doing fractions again. But as far as the specific questions go, it'll just be stuff we've covered after exam 1. Let's dive in with a question related to percents. What is 32% of 575? My hope is today, as we go through these problems, that you see things that look really familiar, things that you've worked on before, whether that was in class, in problems in homework assignments, or on quizzes. Going back through your old quizzes is a great way to find practice problems to help you prepare for the exam, and you should see some like the problems we work on today. My hope is if you had any trouble with problems in the past, that when you see these, you're like, oh yeah, I remember that. I did great with those. Or, oh, I struggled with those. I better ask some questions today. We're not going to have any polls in class, but you are free to ask questions whenever you want to. We'll probably go through the problems fairly quickly because it is a review and it's stuff we have worked on before. But if you have questions, please don't be shy about asking those. Same thing's true over the next day or two. If there are things you're working on in your preparation and you want to ask about those, feel free to send me an email or post on the discussion board. That's just fine. Okay, enough talking. Let's go ahead and dive into these. So our first question here says, what is 32% of 575? What is the thing we don't know? So we'll call that X. Is translates to equals. 32% we'll write as a decimal. Of is multiply, and 575 is just 575. In this one, we don't really need to solve an equation. We just need to multiply here, and we'll do 0.32 times 575 and end up with 184. This question said round to the nearest tenth. Well, our question already is 184. Like this would be a perfectly fine answer. If you happen to write 184.0 because you were being really strict about rounding to the nearest tenth and showing the answer to the nearest tenth, that would be just fine. Canvas should give you credit for an answer like that. And if Canvas didn't, please let me know and I would. The one at the bottom says 54 is what percent of 236? We're going to translate this into an equation. 54 is what percent? That's the thing we don't know. We'll call it X of 236. This one's a little bit different than the one up top. And the one up top, all we needed to do was simplify. We just needed to multiply those two numbers together to get our answer. For this one, we actually have to solve an equation. Now, it's not a very complex equation, but we don't do algebra that often. So when it comes up, I want to make sure to discuss the idea that in order to get this X by itself, we need to get rid of that 236. It's multiply, so we're going to divide by 236 on the right. If we divide by 236 on the right, we also have to divide by 236 on the left. And then on the right-hand side, those cancel, leaving the X. That's what we were after. On the left-hand side, we have 54 divided by 236. And I get a really long decimal that is 0.228813. And it keeps going. We don't want to stop there with this one, though, because looking back at the question, it says what percent. So we want our answer to be in the form of a percent rather than a decimal. So we're going to need to move that decimal over 2 places, and we'll have 22.8813%. And now that we're done with everything we needed to do, at this point, we're going to round our answer to the nearest tenth. So we'll find the tenths place. We'll look 1 space to the right. That's 5 or bigger, so we'll round this up to 22.9%. On a quiz, or excuse me, on the exam, you would just put the 22.9 and not include the percent symbol. Instructions would tell you about that. So 54 is what percent of 236? It's 22.9%. As we go through these, make sure to let me know whenever you have questions. Counting. This is related to the fundamental principle of counting, where find a number of choices for each stage in the problem and then multiply those together. So here we have a license plate consists of 3 numbers followed by 2 letters. The letter I cannot be used. How many license plates are possible? So you don't necessarily have to do this, but 3 numbers followed by 2 letters. I'm going to start out by sort of making myself little labels here so I don't lose track of it. 3 numbers followed by 2 letters. And then I just have to think, okay, well, how many numbers are possible? 1 through 9. Don't forget about 0. There are 10 possibilities for that space. 10 possibilities here, 10 possibilities here, and then the letters are next. Now, there are 26 letters in the alphabet that I would have to pick from. But this problem gave me a little bit of a condition and said the letter I can't be used. So, okay, I can't use I, so that means instead of 26 letters, I only have 25 to pick from. And I have the same 25 to pick from here. Now we've found the number of choices for each space. We're going to multiply these together. And we'll have 10 times 10 times 10 times 25 times 25. And that's 625,000. So a license plate with that structure would have 625,000 possible license plates. The one at the bottom here says, how many of these license plates are possible if we do this without repetition? Meaning repetition's not allowed. Once I've used a number, I can't use it again. Once I've used a letter, I can't use it again. Well, we have the same structure. We still have number, 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 and letter, letter. Same structure, same rules are in place. The letter I can't be used. So we've got to keep all this in mind when we go write down the possibilities for each space before we multiply them together. I have all the numbers possible here. So that works. And now let's see. I'm going to use another number here. I've used a number in that spot. I don't know what the number is, but I know I've used one of them. So I don't have all 10 to pick from anymore. Now I have 9. And then when I get over to this space, now I've used 2 numbers. So I don't have all 10 to pick from anymore because I've used 2 of the numbers. So instead of 10 or even 9, now I only have 8 numbers left to pick from. Okay, now we get to the letters. There are 26 letters in my alphabet. I can't use the letter I, so that gives me 25 letters to pick from here. And now of those 25 letters that are available to me, I've used one. So I don't have all 25 to pick from anymore. I have 24. The reason we count down like that is because of this instruction of without repetition. I'm not allowed to repeat, so that's why my numbers go down by 1. I found the number of choices for each space. Now we just need to multiply those together. 10 times 9 times 8 times 25 times 24 is 432,000. So with this setup and repetition not allowed, I have 432,000 license plates that are available. Makes sense that it would be a smaller number because not being allowed to repeat means I'm going to have less of them. Okay, you let me know if you have questions. I'll try to sort of pause when we get to the end of each page before we move on to give you a chance, but you don't have to wait for me. You can interject a question anytime. Permutations. Remember that permutations are what we're working with when order matters. Permutations come up with words like order or arrange. In this particular situation, we have 8 books and we're going to arrange 5 of them on a shelf. The reason order matters here is if I put my 5 books on, or if I put 5 of my books on the shelf, it would look different if I change the order. Because the bookshelf would look different if I change the order, order matters. Also, we do have a nice keyword in here that says arrange, which is a real strong indication that order matters. When we're working with a permutation, once we've decided order matters, we have a formula that is n factorial over n minus r factorial, where n is the total number of objects and r is the number in use. And in this particular case, we have 8 books total, and we are arranging 5 of them on the shelf. So this is 8p5, or a permutation of 8 things taken 5 at a time. Once you get here, many of you are comfortable using your NPR button on your calculator. And if you are, that's totally fine. You never know what might happen though. Your batteries could die. You might forget how to use that button. So we're going to see how to do this by hand just in case. Also, if you just don't like using that button and you want to do it by hand, that's absolutely fine. So we'll have n factorial over n minus r factorial. And that'll be 8 factorial over 3 factorial. And then from here, we can finish this up. And the way that we're going to do that is I'm going to rewrite 8 factorial. 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I'm going to write that out. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And this is sort of a nice shortcut we get here in that I'm writing 8, 7, 6, 5, 4, 3, 2, 1. But when I get here, I'm going to write 3 times 2 times 1 that way. And the reason that I do that is because in my denominator, I have this 3 factorial, and those will cancel each other out. And now all I've got is 8 times 7 times 6 times 5 times 4. And there are 6,720 ways that we can arrange 5 of 8 books on a shelf. Big numbers here. It feels like, gosh, that's a lot. Well, if we started listing them out, and we did that when we first studied permutations, you'd see, sure enough, okay, I'm convinced that there's a whole lot of them. In addition to permutations, we talked about combinations. And the key to combinations is that order doesn't matter. What that means is, in a situation like this one, there are 12 students in a class and 5 of them will be chosen to clean the room. How many ways will they be chosen? Now, it doesn't matter if you're the first student chosen, the third student chosen, or the 5th student chosen. The order in which you're picked makes no difference. You're either cleaning the room or you're not. Order has no impact on this. So this is a circumstance where order doesn't matter. That tells us we have a combination. There's also a nice keyword in here that is chosen. If you're just choosing or selecting or picking things, those verbs don't really indicate that we have an order to them. That those sort of let us know that order doesn't matter. And that gives us a combination. And we have a formula for that as well. It's very similar to the formula for permutations, but it is a little bit different because of that r factorial at the front in the denominator. In this particular case, I have 12 total students, and we're choosing 5 of them to clean the room. So a combination of 12 things taken 5 at a time. You might say 12 choose 5 for that if you're really being shorthand. Here we'll have 12 factorial over 5 factorial and then 12 minus 5 factorial. This will simplify to 12 factorial over 5 factorial, 7 factorial. Oh, again, if you're very comfortable with your NCR button on your calculator, feel free to use that. But just in case, we're going to work it out by hand also. Once I get to this point, I'm going to rewrite 12 factorial out. 12, 9, 8, 7, 6, 5, 4, 3, 2, 1. I could stop here at 5 factorial, but I'm going to pick whatever the bigger number is and stop there. So when I rewrite this, what I'm going to do is I'm going to have 12, 11, 10, 9, 8, 7 factorial on the top. And that's because I have this 7 factorial on the bottom that'll cancel with that. This 5 factorial that I have down here, I'm just going to go ahead and write that out. These 7 factorials cancel. And now in the numerator, I have 12, 11, 10, 9, 8. In the denominator, I have 5, 4, 3, 2, 1. So we'll go ahead and multiply. 12 times 11 times 10 times 9 times 8. That gives me 95,040 on top. And 5, 4, 3, 2, 1 is 120 on the bottom. And we can divide those. I'm going to make myself a little space here. There we go. So 95,040 divided by 120 gives me 792 ways that 5 of 12 students can be chosen to clean the room. For those of you who really like canceling, which may not be very many, but that's okay, you could say, well, dividing by 1 doesn't do anything. And well, 5 times 2 will get rid of that 10, and 4 times 3 will get rid of that 12. So really, all I have here is 11 times 9 times 8. And 11 times 9 times 8, sure enough, 792. You can also feel free to use your combinations button on your calculator if you're comfortable with that. It's totally fine. After we moved on from the fundamental principle of counting, we started talking about probability. And the most important thing about probability, remember, is that probability is equal to successes over outcomes. Anytime we're doing a probability question, no matter how simple or complex it might be, we're looking for successes over outcomes. Basic examples would be a single 6-sided die is rolled. Find the probability of getting a 2. That's what that notation represents there. Okay, well, this is successes over outcomes. So I know on a single 6-sided die, there are 6 outcomes. And the successes aren't necessarily something good. They're the thing that I'm looking for. How many ways is it possible for me to get a 2? Well, there's only 1 2 on that die. So there's 1 success out of 6 outcomes. So the probability of getting a 2 is 1 out of 6. The probability of getting an even number. Again, we're looking for successes over outcomes, and we have 6 outcomes on this die. And then if I want to find the probability of getting an even number, I need to know how many ways there are to get an even number. You might not need to do this, but writing out the sample space can sometimes be helpful. And we can see there that there are 3 even numbers on the die. So there are 3 successes out of the 6 outcomes. So the probability of getting an even number is 3 out of 6. If you're thinking, could that be reduced to 1/2? Absolutely, it can, but it doesn't have to. Either one of these answers would be considered correct on the exam. With probability questions, you can reduce if you want to, but you don't have to. A little more involved would be probability questions involving a deck of cards. Dice and cards are great setups for probability questions. And a single card is selected at random from a standard deck. Our first question here says, find the probability of getting a card that is black and a 7. A little bit of knowledge of a deck of cards here is helpful. If you need to jot some things down on your page of notes, you absolutely can. Remember always, though, that probability is successes over outcomes. So what we're looking for is successes over outcomes. And in my standard deck, I have 52 cards. I'm going to pick one of them. So there are 52 outcomes. Now we just need to figure out how many successes there are. How many cards there are in the deck that are black and a 7. Well, let's see. We could have the 7 of clubs would be a black card and a 7. The 7 of spades would be a black card and a 7. The word and is really important to us here. In order to satisfy and, we need to find cards that meet both of those conditions. It has to be black and it has to be a 7. Reason I mention that is, well, what about the 7 of hearts? You might be thinking. Well, the problem with the 7 of hearts is, yes, it is a 7, but it's not a black card. So as far as this question goes, it's no good. We have to meet both conditions to be a success. And so 7 of clubs, 7s of spades, that's it. We only have 2 successes out of 52 outcomes. So the probability of getting a card that is black and a 7 is 2 out of 52. The question on the bottom of this page is extremely similar to the one we just did. The only difference is it says or instead of and, but it's a very important difference. The probability of getting a black card or a 7. Now, because the word or is in here, we don't have to have both things happen. We just need to have at least one of those things happen. If we get a card that is a black card, that's a success. If we get a card that is a 7, that's a success. And so we need to count up all of those. Now, we're still going to have 52 outcomes. But in order to find our successes, if a card is black, we count it. If a card is a 7, we count it. So first thing we can do is we can count all the clubs, and there are 13 of those. And we can count all of the spades, and there are 13 of those. So far, we've already included the 7 of clubs and 7 of spades. We don't want to count those twice. So on top of these 26 cards that I have so far, now I get to throw in the 7 of hearts and the 7 of diamonds. And so all together here, I end up with, let's see, 13, 26, 27, 28 successes out of 52 outcomes. So the probability of getting a black card or a 7 is 28 out of 52. You might be asked to give probabilities as fractions. You also might be asked to give them as decimals. And let's just say that in this one we just worked on here, this one at the bottom, let's say we were asked to give that as a decimal. All we've got to do is one more step. This 28 over 52 is just 28 divided by 52. And rounded to the nearest hundredth, we would have 0.54. So if you were asked for this as a fraction, you'd give 28 over 52. You could reduce it if you want to, but you don't have to. If you were asked for this as a decimal rounded to the nearest hundredth, you would answer with 0.54 or 0.54. That's fine too. Again, let me know if you have questions. Otherwise, I'll keep moving right along. Probability from a table. This is another type of probability where we've got information given to us in the form of a table. And what we've got here is where do we get 28 from? The 28 came from the fact that we have, when we're looking for our successes, we have 13 clubs that are black cards, so we count those. We have 13 spades that are black cards, so we count those. And then we want to make sure to also count any other 7s that we haven't counted so far. And so we include the 7 of hearts and we include the 7 of diamonds. So that's 13, 26, 27, 28 total cards. Perfect. Very good. All right. So here, we've been given data on how children get to school, and some of them take the bus, some of them ride in a car, and one person from this entire table is going to be selected at random. Our first question here says, what is the probability that one person selected at random is a girl? Again, remember, and I'll say it over and over again, that probability is successes over outcomes. So the first thing we need here is our total number of outcomes. So let's see, our total in this chart will be 9 plus 5 plus 3 plus 8. It looks like there are 25 total students that were in this data. And so our number of outcomes is going to be 25. We're picking one person at random. The probability that that person is a girl, well, then we need to look at the girls row here and add up all those girls. And it looks like there are 11 girls out of 25 total students. So the probability of selecting a girl is 11 out of 25. Our next question is, what's the probability a student rides the bus? We still have 25 outcomes here. Now we're looking at students who ride the bus. And it looks like there are 9 plus 3, 12 of those. So the probability that the student would ride the bus would be 12 out of 25. And then finally, this last one down here, a boy who rides in a car. So for this one, we still have all 25 outcomes, but now we're being really specific about it. We're looking for boys who ride in a car. So boys who ride in a car, there's 5 of those. And so the probability of getting a boy who rides in a car is 5 out of 25. I remember probability from a table going extremely well when we did those. So my guess is the same thing is true here. We got to the topic of simulations, and we did a lot of sort of experimental probability with those. And if you're thinking, how in the world could you ask us a simulation question? Because we might all get different answers. You'd be exactly right. Using a random number table to do an experiment, you might all get different answers. So that would be really hard to ask. Instead, we can do something like this. According to the city, a certain stoplight is red 70% of the time. You're going to drive up to the stoplight every day for the next week. If you were going to do a simulation with a random number table to determine the number of times the light will be red, how many digits would you assign to red? So this isn't about performing the simulation. This is about setting it up. And our question here is, how many digits would you assign to red? Keeping in mind that our random number table has these digits on it. It has those 10 digits on it. How many of those do we want to assign to red? Well, the stoplight is red 70% of the time. So we want to give 70% of the digits to mean red. Doesn't necessarily have to be these 7 right here, but that's one way to go. Because we want to give 70% of the digits to red, we want to give 7 of the 10 digits to red. So we want to assign 7 digits to red. Don't overthink a question like this. It's exactly what it sounds like. It's red 70% of the time, so I want red to be 70% of the digits, or 7 of them. Just don't overthink a assigning digits question. As we continued to work through probability, we got to successive events, one after another. Sure thing, Eskadar. We want to know, our question on this one is, if you were going to do a simulation, so if you were going to do a simulation, how many digits would you assign to red? There are 10 digits total that are possible on a random number table. These are them. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 digits total. We're going to assign those digits to either mean red, yellow, or green. And it doesn't say anything about yellow or green in here. It's strictly, how many are you going to give to red? Well, the light is red 70% of the time. So we want to give 70% of the digits to red. And 70% of the digits then would be 7 out of 10. If you wanted to write down some kind of equation for this, you could say, what is 70% of 10? And then solve it. And, x is 0.7 times 10. And then you'd find out that we want to give 7 of the digits to red. So, if you'd like to set up an equation to solve, you can. But honestly, if it's 70%, that's going to be 7 out of 10. And I'm not going to ask you which digits. Yeah. The answer is just 7. That's it. All right, very good. After we talked about the probability of a single event, we talked about the probability of successive events, things that happen one after another. A jar contains the following marbles: 7 red, 2 orange, 3 green, and we are going to pick 2 marbles. One after the other. The first question here says, find the probability of getting orange followed by green with replacement. That means after I pick out the first marble, I'm going to put it back in the jar, and then we'll pick the second one. So I need orange followed by green. Now, when I have successive events, this is very similar to the fundamental principle of counting. We're going to find the probability of each event and then multiply those probabilities together. So here, what I want to find is the probability of getting an orange marble and the probability of getting a green marble, and then multiplying those together. And so on that first draw, the probability that I'm going to get an orange marble, well, let's see, successes over outcomes. So I'm going to need the total. Total here is 7, 8, 9, 10, 11, 12. So the probability that I'll get an orange marble on that first draw, I have 12 outcomes, and I have 2 successes. So the probability of getting an orange on that first draw is 2 out of 12. I'm going to replace it. I'm going to put it back in. So for that next draw, I'm going to have 12 outcomes. Now I'm looking for finding a green one. There are 3 of those. So the probability of getting a green is 3 out of 12. And now that I know the probability of getting orange, the probability of getting green, I'm going to multiply those together. Now 2 times 3 is 6. In the denominators, 12 times 12 is 144. So the probability of getting orange followed by green is 6 out of 144. You could use a tree diagram here if you're thinking, I thought we did tree diagrams with these. You could, but you don't have to. And the reason you don't have to is because what we're after here is one single specific outcome. Orange followed by green. That's it. I'm not looking for any other successes. This would be one of the paths on my tree diagram if I were to draw it. But because I'm after one single specific outcome, all I need to do here is find the probability of each event and multiply them together. For the one on the bottom, probability of green followed by red. This is being done without replacement, meaning after I pick that first marble, I'm going to leave it out and then pick another one. So the probability that the first one's green, that's going to be 3 out of 12. And then I'm going to take that green one and leave it out. So I don't have 12 marbles in my jar anymore. I only have 11 for that second draw. I need to get a red one there, and I have 7 red ones in the jar out of the 11 that are possible. So the probability of getting red there is 7 out of 11. So the probability on the first draw is 3 out of 12 of getting a green. The probability of getting a red on the second draw after leaving that first marble out is 7 out of 11. And now we can multiply those together. 3 times 7 is 21. 12 times 11 is 132. And so the probability of getting green followed by red would be 21 out of 132. Another type of successive events problem would be, real world events that actually take place. There's a 65% chance that it would be cloudy tomorrow. And if it is cloudy, there's a 40% chance that it will rain. So our successive events here are the first thing that happens is that it's cloudy. And then the next thing that happens is that it will rain. And if we want it to rain, we need both of these things to happen one after the other. And so these are successive events. So we're going to find the probability of each event and then multiply those together. This is another case where be careful not to overthink it. We don't have fractions here with successes over outcomes. Instead, we were just given the probability right out of the gate. The probability that it's going to be cloudy is 65%. So we'll write that as a decimal. The probability that if it is cloudy, the probability of rain is 40%. So we'll write that as a decimal. And in order to find the probability of two things happening one after another. Here, it's cloudy and then it rains. Find the probability of each event and then multiply those together. And so we'll multiply these and have 0.65 times 0.4, which is 0.26. So what's the probability it's going to rain tomorrow? 0.26. No problem, Escadar. I have a cat that likes to lay on my keyboard, and these things happen. Sometimes it's just our own fingers, but I totally understand when that happens. Usually for me, it's a cat. Probably the most challenging, I gotcha. Probably the most challenging question that we will work on in preparation for this exam are the gumball questions involving tree diagrams. A gumball machine contains 6 red and 4 blue gumballs. You're going to buy 2. Find the probability of at least 1 red, and then we'll work on the other 2 questions after that. I want you to notice that here we need the tree diagram because we don't have a single specific outcome. If we were asked for the probability of getting red followed by blue, well, we wouldn't need the tree. Then we could just use the same approach we used with our jar of marbles a couple of pages ago, where find the probability of each event and multiply together. But these are not single specific outcomes. These are, there's probably more than one way to do it. I better make the tree. And so let's go ahead and make our tree, and then we'll answer these questions. We start out buying that first gumball, and it's either going to be red or blue. And we need to put the probabilities on here. Let's see. There are 10 total gumballs, and 6 of them are red, and 4 of them are blue. And so the probability of me buying a red one would be 6 out of 10. The probability of me buying a blue one would be 4 out of 10. And now we'll look at buying that second gumball. When I go to buy the second gumball, if I'm up here, that means the first one was red, and then the next one is either going to be red or blue. And we can put those probabilities on. And keeping in mind, I bought a red one. It's no longer in the jar. It's no longer in the machine. So now I have 9 gumballs left in the machine. I started with 6 red. I bought a red. So now there are 5 reds left. The probability of me getting another red one would be 5 out of 9. To put this probability in place, there's going to be 9 gumballs in the machine. I started with 4 blue. I bought a red one. So there's still 4 blue in there. Down here on the bottom half, if I'm down here, that means the first one I bought was blue. We'll keep that in mind as we put the probabilities on. The second one could either be red or blue. Okay, so I bought one, it was blue. So now I have 9 gumballs in the machine. I started with 6 red. The one I bought was blue, so all 6 reds are still in there. So the probability of getting a red here is 6 out of 9. At the very bottom, I started with 10, I bought one, now there's 9. I started with 4 blue gumballs, I bought a blue one. So now there's only 3 left. So the probability of getting a blue one is 3 out of 9. And now I have, my tree is built, all my probabilities are on there. Now I'm going to create my sample space by multiplying. What I mean by that is, if I go red, red, that puts me with the outcome red followed by red. And the probability of that is what I get when I multiply the probabilities along that path. When I multiply, let's see, 6 times 5 will be 30. 10 times 9 will be 90. So I could end up with red followed by red, and the probability of that is 30 out of 90. Okay, continuing down my tree, the next one, I could do red followed by blue. Red followed by blue. I need to multiply the probabilities along that path. And 6 times 4 in the numerator is 24. 10 times 9 in the denominator is 90. It's kind of nice. My denominator is going to be the same every time. All right, I could do blue followed by red. And we'll multiply those. 4 times 6 will be 24. 10 times 9 will be 90. And then finally, the one at the very bottom, blue followed by blue. I'll multiply the probabilities along that path. 4 times 3 in the numerator is 12. 10 times 9 is 90. Now, at this point, I've created my sample space, and I know all the probabilities that go with them. I'm done multiplying. Any multiplying I'm going to do is over. Multiplying happens when I have one event followed by another. Okay, we've done all that. Now we have our sample space, and we just need to go answer the questions based on what they ask for. The first one says, what's the probability of getting at least one red? You want to be careful here when you identify your successes. At least one red. Well, this one has 2 reds in it. So that is a success. So we want to count this one. Red followed by blue, that has at least 1 red. Blue followed by red, that has at least 1 red. Blue followed by blue, that does not have at least 1 red. So I could get at least 1 red this way, or this way, or this way. Or union, join them together. We need to join all these together, and the way we'll do that is we're going to add those probabilities together. We're going to add the different ways that I could possibly get at least 1 red, and that's those 3 ways. And so we're going to add those 3 together. 30 over 90 plus 24 over 90 plus 24 over 90. When we add fractions, our denominator is going to stay the same and just be 90. And we add the numerators together. And we'll have 30 plus 24 plus 24. And that's 78 out of 90. So the probability of getting at least 1 red is 78 out of 90. We haven't talked about binomial probability yet. It's coming up, but exactly 1 red. Exactly 1 red is very similar to at least 1 red, but it's not the same. Exactly 1 means exactly 1. No more, no less. And so when I want exactly 1 red, this one, there's a red in there, but that's 2 reds. That's no good. 1 red, 1 blue. Exactly 1 red, yes. 1 blue, 1 red, exactly 1 red. And that doesn't have any reds. So I could get a success this way or this way. And so those are the 2 things I'm going to add together to come up with my probability here. It's just going to be 24 over 90 plus 24 over 90. And when I add those together, that's going to be 48 over 90. Last one. What is the probability that the second one is blue? So I just have to look at my outcomes here, and red, red, no good. Red, blue, yes, the second one's blue. Blue, red, there's a blue in there, but it's the first one, not the second one, so that's no good. Blue, blue, yes, the second one is blue, so I want to count those. So I'm going to add these together and have, let's see, that'll be 24 over 90 plus 12 over 90 is 36 over 90. Content-wise, I think that's probably these are the most challenging questions that we will encounter. You may disagree. You may think, hey, I'm totally comfortable with these. Great. That's fantastic. Very good. I do think some practice is a good idea. Make sure you're comfortable with them and let me know if you have questions. Expected value. Expected value is built around a formula that was expected value is the probability of the first result multiplied by whatever that result happens to be, plus the probability of the second result multiplied by whatever that result happens to be. And we do this until we get to the end of our results. In this particular setup, a jar contains 5 blue, 4 red, and 11 white marbles. If you pick a blue one, you win $5. If you pick a red one, you lose $1. If you pick a white one, you lose $4. Rounded to the nearest hundredth, what's the expected value of playing this game and picking out 1 marble? When we did these, we set up a little table that had our results and the probabilities that go with them. Our results here, we're either going to win 5, lose 1, or lose 4. And now we need the probabilities of each of those. Probability is still successes over outcomes. In order to win 5, I would have to pick a blue marble. There's 5 of those out of, well, I'm going to need my total. 5 and 4 is 9, 11, there are 20. So the probability of picking a blue marble and winning $5 is 5 out of 20. If you see something that you're not sure of where it came from, don't hesitate to ask. And let's see. the probability of losing $1, which means I picked a red marble, would be 4 out of 20. And then finally, the probability of losing $4, which means I picked a white marble, is 11 out of 20. Once I have my results and my probabilities, now I'm ready to use my formula. And using that formula, the expected value will be, okay, 5/20ths of the time, the player is going to win $5. 4/20ths of the time, the player is going to lose $1. And 11/20ths of the time, the player is going to lose $4. Now I just need to simplify this, and I'll have my expected value. Just a little bit of refresher with fractions. When we're multiplying a fraction times a whole number, it can be helpful to rewrite that whole number with a denominator of 1, just to sort of help us in the multiplying process. Because now we're just going to multiply numerators together, multiply denominators together. Here I have 5/20 times 5/1. That'll be 25/20. 4 times -1. That negative is really important. That'll be -4/20 times 1. And then 11 times -4 will be -44/20 times 1. Kind of nice. I already have a common denominator, so adding these isn't going to be too much trouble. I know I'm going to end up with 20 in the denominator. Now I just need to add those numerators. 25 minus 4 minus 44 is -23. And so my -23/20. When we do expected value, we are going to write that in the form of a decimal. And we're going to go ahead and divide here. And I get -1.15. This question said round to the nearest hundredth, so this already is. So the expected value for playing this game is to lose $1.15 per play. It doesn't mean you're going to lose $1.15 on one individual outcome. Remember, expected value is over the long run. What could you expect to happen? If you played this game a whole bunch of times, you would expect to lose $1.15 per play. Binomial probability. Now we're getting to the stuff that should feel more recent. And maybe that makes it more comfortable. Maybe it just makes it more recent, but it should feel more recent. Binomial probability. A family wants to have 5 children. What's the probability of getting 4 boys and 1 girl? Binomial probability is when there are only 2 outcomes. Boy, girl, heads, tails, that kind of activity. And so having 5 children, we only have 2 outcomes, boy, girl. And what's the probability of getting 4 boys and 1 girl? So they're going to have 5 children total. So we are going to use row 5 of the Pascal's triangle over here. We're going to use row 5. I'm going to wipe that out so I have a little space. So we're going to use row 5, and row 5 would be right here. Easy way to identify which row you're in is to look at the first number that's not a 1. That'll tell you which row you're in. You'll see those labels over there, row 1, row 2, row 3, row 4, row 5. So the first number that's not a 1 will let you know which row you're in. And so here we're looking at row 5, and the numbers in there are 1, 5, 10, 10, 5, 1. What those represent are the number of ways to have a certain outcome happen. And what those outcomes are is this first one would be the way to have all boys. So that could be, or wait, Lorraine wants me to do no boys. No boys and 5 girls. 5 would be the number of ways to have 1 boy and 4 girls. 10 would be 2 boys and 3 girls. 10 would be the number of ways to have 3 boys and 2 girls. 5 would be the number of ways to have 4 boys and 1 girl. And 1 would be the number of ways to have 5 boys and no girls. And so you don't have to label both boys and girls here if you don't want to. I find it to be helpful, but really you could just say, well, this is no boys, 1 boy, 2 boys, 3 boys, 4 boys, 5 boys. And if you do that, you've got good enough labels to answer this question. Some of you might like to have it fully complete though and say, okay, wait, they're having 5 children. If they have no boys, then that's 5 girls. 1 boy is 4 girls. 2 boys is 3 girls. 3 boys would mean 2 girls. 4 boys would mean 1 girl. And 5 boys would mean no girls. This is a probability question, so we're looking for successes over outcomes. And if there is 1 way to do this, and 5 ways to do this, and 10 ways, and 10 ways, and 5 ways, and 1 way, what it means is the total number of outcomes here is what we get when we get the sum of all of those numbers. When we add all of them together, that's going to give us our total number of outcomes. And so we'll add those together. 1 plus 5 plus 10 plus 10 plus 5 plus 1, that's 32. So I have 32 outcomes here. So when I write my probability, I know I'm going to have 32 in my denominator. Then I'm looking for the probability of having 4 boys and 1 girl. So I just kind of look down here and I have 4 boys and 1 girl. There are 5 ways to do that. So I have 5 successes and 32 outcomes. So the probability of having 4 boys and 1 girl is 5 out of 32. I may have gone into more detail than you needed on that because binomial probability went fantastic when we worked on them. Let's look at one more. A family wants to have 4 children, so we're going to work on row 4 this time. What's the probability of having at least 3 girls? And the reason that we're doing this question is because the word's at least right here. If we look at row 4, that's 1, 4, 6, 4, 1. Since this question asked about girls, I'm going to do my labeling in terms of girls. And this will be the ways to have no girls, 1 girl, 2 girls, 3 girls, 4 girls. You could label it with the boys if you want to. That would be 4 boys, 3 boys, 2 boys, 1 boy, and no boys. And then we go answer our question. What's the probability of at least 3 girls? Well, since it's a probability question, I'm going to need my total number of outcomes. So let's get that. 1 plus 4 plus 6 plus 4 plus 1 is 16. So I have 16 outcomes. And I need to figure out how many are successes. Be careful here. At least 3 girls. So right here is 3 girls. That would be exactly 3 girls. But this said at least. So 3 or more would be considered successes. So 3 girls is a success. 4 girls is a success. So altogether we have 5 successes out of our 16 outcomes. And so the probability of at least 3 girls is 5 out of 16. All right. Now we get to move into geometry. We didn't spend a ton of time on geometry, but we did do a few things, and we'll just do some review. First, definition of polygon. It's a simple closed figure made up of line segments. Simple does not intersect itself. So I can have any kind of goofy shape. If it doesn't intersect itself, then it's simple. If it does intersect itself, then it's not simple. And as far as closed goes, if it starts and ends at the same point, when I draw it, if it starts and ends at the same point, it would be closed. But something like this is not closed because when I drew it, I didn't start and end at the same point. We looked at definitions of a bunch of different quadrilaterals and triangles. My favorite question for these, as far as those definitions go, are true-false questions. And to be fair, these true-false questions can be fairly challenging. Our approach to these is to look and see if we can find a counterexample. If we can find a counterexample, then we can say it's false. All we need is one counterexample to say that it's false. So this first one up here, all parallelograms are rectangles. Now, is it possible to draw a parallelogram that is a rectangle? You bet. There's one right there. Because this top and bottom are parallel, left and right are parallel. That's a parallelogram, and it's a rectangle. Sure, it's possible, but this didn't say, is it possible? This said all parallelograms are rectangles. So what I'm doing, my approach here is I'm going to try to find a counterexample. I'm going to try to draw a parallelogram that is not a rectangle. And if I can do that, then I can say false. And I can draw a parallelogram like this, where top and bottom are parallel, left and right are parallel, but that is not a rectangle. And all parallelograms are rectangles means all of them. Well, I just found one that's not, so that statement is false. And here's my counterexample so that I'm positive my answer is correct. On the bottom, it says all squares are rhombuses. Okay, I'm looking for a counterexample. I'm going to draw a square that's not a rhombus. That's how I'm going to find a counterexample. So I'm going to draw myself a square. Squares have 4 right angles. They have 4 sides the same length. Okay, well, that one's a rhombus because all 4 sides are the same length. Okay, what if I draw a really big square instead? And now all 4 sides are the same. Wait a minute. Every time I draw a square, all 4 sides are going to be the same length. That's what a rhombus is. Every time I draw a square, it's going to be a rhombus. I'm never going to be able to find a counterexample, so that statement is true. This is our approach. This is our strategy. Look for a counterexample. In the process of trying to get that counterexample, you may convince yourself that the statement's true. We also did this with triangles. Every equilateral triangle is acute. I got to remember what an equilateral triangle is. Equilateral means all the angles are the same, all the sides are the same. Every equilateral triangle is acute. Same approach. I'm looking for a counterexample. I'm going to try to draw one that's not. So if I draw an equilateral triangle with all sides the same length and all angles the same, well, acute means all the angles are less than 90. And in this triangle, all the angles are 60. So yeah, that one's acute. All right, let me draw a bigger equilateral triangle. Wait a minute here. Every time I draw an equilateral triangle, all the angles are the same, which means all the angles are 60. Every equilateral triangle I draw has to be acute because all the angles are less than 90. Okay, every equilateral triangle is acute. That is true. Down at the bottom, all isosceles triangles are scalene. Okay, I got to remember isosceles means at least 2 sides the same length. So if I draw an isosceles triangle down here with 2 sides the same length, scalene means all sides are different. Well, all isosceles triangles are scalene. Scalene means all the side lengths are different. Here, I've got an isosceles triangle with 2 sides the same. Right here's my counterexample. So this must be false. In fact, no isosceles triangles are scalene because by definition, isosceles mean they have at least 2 sides the same. Scalene means they all have to be different. So that one's definitely false just by the definitions of the 2 words. We talked Pythagorean theorem, which when you have a right triangle, you can say that the measure of one leg squared plus the measure of the other leg squared equals the measure of the hypotenuse squared. Find the missing leg of a right triangle with one leg 8 feet long and a hypotenuse of 14 feet. You don't have to draw a picture. I typically do anytime just to sort of give myself a little sense of it. One leg is 8, the hypotenuse is 14, and I'm looking for the other leg. So we'll set up our Pythagorean theorem question here. Leg squared plus leg squared is hypotenuse squared. I can simplify a little. X squared plus 64 is whatever 14 squared is, 196. We've got an equation to solve here. To solve this equation, I need to get x by itself, which means I need to get the term with x by itself. So the first thing I need to get rid of is that 64 on the left-hand side. So we're going to subtract 64 from both sides. On the left-hand side, they cancel, leaving me with just x squared. On the right-hand side, I have 132. Last thing I need to do here to get x by itself, I got to get rid of squaring, and to do that, I'm going to take the square root. If I take the square root of the left, I take the square root of the right. On the left-hand side, those cancel, leaving me the x. On the right-hand side, I have the square root of 132, which is 11.48912. In this one, I was told to round to the nearest hundredth. So I'll find the hundredths place, look one space to the right. That's 5 or bigger. So we're going to round this up to 11.49. So what is the length of this leg down here? 11.49. It would be feet, but you wouldn't include feet with your answer on the exam. Very recently, we talked about the distance formula and finding the distance between 2 points. And that formula looks like this. The distance between 2 points is x2 minus x1 squared plus y2 minus y1 squared. It's an offshoot of the Pythagorean theorem. And I think the easiest way to handle this is to just go ahead and label the points that you're working with. x1, y1, x2, y2. You could reverse those names. You could make the first one x2 and y2 if you wanted to. Just make sure you keep your 1's together and your 2's together. And so we'll find the distance between these 2 points. And that'll be, let's see, my x2 is -3 minus 2 squared. My y2 is 5 minus 6 squared. Now we just need to simplify this. I think the biggest danger in these is the negative signs. So be really careful when you're working with the positives and negatives here. -3 minus 2, that's going to be -5 squared. And then 5 minus 6, that's going to be -1 squared. The parentheses around those numbers are really important because we're squaring the entire thing. The -5 is getting squared, not just the 5. So keep those parentheses around there, and our distance will be, let's see here, -5 times -5, -1 times -1. And so our distance between these 2 points will be the square root of 26. I'll find the square root of 26. And I get 5.099. I was told to round this one to the nearest tenth. So we'll find the tenths place. And we'll look one space to the right. That's 5 or bigger, so we're going to round this up to 5.1. The distance between those points is 5.1. Very recently, we would be given a figure, and from that figure, we would be given some information, and what we'd have to do is find the measure of some angle that we didn't know at the beginning. In this particular case, we are given this sort of triangle shape here. We can see a vertical and horizontal. That's a right angle over there. And what I know is that this angle measures 130 degrees. What we're asked to find is the measure of angle CAB. The first thing we have to do is identify angle CAB. So it's this angle here that we're looking for. All right. So I know some things, but I don't know everything. Let's see. One thing I can do here is I can see on this picture that these two angles, the one I've been given plus this one, make a straight angle. And I know that a straight angle is 180 degrees. That's a very valuable tool for me in my box. So if these two together are 180 degrees, then this one over here must have a measure of 50 degrees. All right, well, that's still not getting me over there to angle CAB. Well, now as I look at my figure, what I happen to notice is that right here, I have these two angles. They share a vertex and they don't share a side. Those are vertical angles, and vertical angles are equal. So that means if this one's 50 degrees, then this one over here must also be 50 degrees. I still don't have the measure of angle CAB, but now what I know is the three angles of a triangle add up to 180. So if I've got 90 and 50 and this one, those three have to add together to make 180. So if 90 plus 50 plus the one I don't know have to add up to 180, that means, let's see, that's 140 plus the one I don't know has to add up to 180. Subtract 140 from both sides, and the angle I'm looking for must have a measure of 40 degrees. I don't think those are always easy, but I do think as long as you keep the idea in mind that straight angles add up to 180, the three angles of a triangle add up to 180. The complementary angles add up to 90. Supplementary angles add up to 180. And vertical angles are equal. Those five things will be the tools we use in our toolbox to work through problems like that one. One last thing. You would have seen this before. You'll probably see it again in a few weeks when we get to exam 3. What I want you to do as you go into this exam is be realistic and positive. Do not be a perfectionist or be negative. One thing to think is there's an impossible amount of things to learn for this test. Well, I don't know. We just did a pretty comprehensive review in one class meeting. So impossible, definitely not true. Realistic side, I don't need to know every question to pass. That's totally true. You don't. I want you to get every question right. That's what I'm hoping for. But if you don't get every question right, you can still pass, and heck, you can still even earn a really good grade. My knowledge of fill in the blank is shaky. That might be true. Hopefully when we went through it all today, you're kind of like, you know what? I didn't get that before, but now it makes perfect sense. That's where I hope you are. Even if you're not, you've got a little time before the exam is due and some time to study to sort of fill in any gaps. The negative thoughts, I always do poorly on tests. Always is a very big word. I bet I can find one counterexample where you've done well on a test somewhere along the line, and perhaps you've just felt really comfortable with this content. Perhaps you've studied great. Perhaps you plan on putting in a lot of time between now and when your exam is. If I don't pass this test, I'm a failure. That's the one that is the most absurd on this whole page. This is one test in one math class in one semester. It does not in any way define your value as a person. I'm going to pass this test, but if I don't, I can bounce back. That's true. I mean, we still have 4 weeks of class left after this. There are several quizzes left. There's another exam down the road. So even if you don't do a great job on this test, there's still opportunities out there to improve your overall grade. This test is going to have a trick question. I promise you it won't on purpose. There may be true-false questions that are challenging. The gumball questions may be challenging, but I'm certainly not trying to throw something at you that you wouldn't be prepared for. I'm definitely not trying to trick you. And then my favorite of all the things on this page, this test is designed to let me show what I know. Maybe you struggled with a concept the first time we looked at it. Maybe you did a little better on the quiz, but you still didn't have it perfect. But now you have another chance to say, you know what? I didn't have it then, but I've got it figured out now. And this is a chance for you to show that. So I'm hoping that you can look at this as an opportunity rather than something that is sort of ominous. You want to prepare. You want to be confident when you go into it and do your best. And that's what I hope happens.